Ladies and gentlemen, my name is Hamid Bouchair. I am from Université Clermont-Auvergne in Clermont-Ferrand, France. I will present you today the work prepared by my PhD student Sabra. She is from University of Tunis and she is preparing a PhD thesis in co-tutel between the two universities. The work is oriented on an experimental and numerical study on steel web panel representing the compression zone in beam-to-column connection. Regarding the component method of Eurocode 3, the beam-to-column connections are characterized by main component, tensile zone, compressed zone, and shear zone. To represent the compression zone of connections, direct compression tests on web panel with different geometries are performed. The test is realized in double compression as shown on this figure on the right part of the screen. The summary of the presentation is organized on different parts: an overview on the experimental tests, the numerical modeling, and the comparison between finite element model and experimental tests to validate the finite element modeling. Parametric study is performed on the influence of the length of the partial stiffness on the web panels. The experimental tests are realized on two campaigns with 2 dimensions on length. 2 testing devices are used. The first campaign concerned the small specimens with partial stiffness and unstiffened panels, 500 mm length. The large specimens on the right are with length of about 3 meters. They are unstiffened or fully stiffened with double stiffeners. The measurement concerned the load, the vertical displacement, and the out-of-plane displacement on the web panel, mainly for the large specimens. The specimens of the 2 campaigns are defined in this figure. The mechanical characteristics of the steel in all parts of the tested specimens are defined on coupling tests taken from the web, the flange, and the stiffeners. Here we have the characteristics of the materials, elastic limit and ultimate limit. The thicknesses and dimension of the web and stiffeners are given here. We have various parameters on this point of view. This is the unstiffened specimen, and the full stiffened specimen are here with stiffeners welded to the flange and the web. And here we have the partial stiffeners at one end, at the central part, and on 2 parts. For this case and this one, the stiffener is welded to the flange. The free length of the web panel here is equal to the free length here. But here the free length is equal to half this distance because of the position of the stiffener. We tested 24 specimens for 6 different configurations. A numerical model is prepared to represent the behavior of the tested specimens. It is based on shell elements with material and geometrical nonlinearities. Here we have the example of a stiffened specimen with, in one part we have the support, and on other part we have the surface, the loaded surface. The load is controlled in displacement, and it is performed on 2 steps. The first one is based on an Eulerian calculation to define the initial imperfection based on eigenvalues and eigenvectors analysis. And the second part is based on large displacement nonlinear calculation. Different parameters are evaluated: the mesh densities, the finite element types, the initial imperfection magnitude, and the material source. Here we can see the example of material loss. We compared elastic perfectly plastic model and elastic plastic with strain hardening representing the real behavior of the material. and the tests. Here we can compare the influence of the simplification of the model, as in the main cases we use the elastic perfectly plastic model. To validate the numerical model, it is compared with the tests considering the load displacement curve and also the failure mode. Here we show the case of unstiffened panel with the same parameters as the other cases stiffened. And we can see that the finite element model represents well the behavior, except the initial stiffness, which is complicated to evaluate as it depends on the boundary conditions of tests and those of the finite element model. The observed failure mode is buckling, flexural buckling with elastic plastic behavior. And here we have another geometry with higher slenderness. And we can see that the instability here is defined by a kind of sharp decrease of the load. The fully stiffened panel, one stiffener in each side of the web panel, showed the highest values of resistance. Here we have 1,200 kilonewton, which is about double of the same specimen without stiffeners. Here it's another geometry. If we compare with the unstiffened element, we have at least double of the resistance. The failure mode reached here is in torsional buckling because of the presence of stiffeners. And the instability here is observed with the decrease of the load, but with large plastic deformation as seen here in this part. The finite element model represents well also the behavior of the specimen regarding the load displacement curve, except stiffness here, and also the failure mode. Another case of comparison concerned here the stiffener on one side only of the web panel. We can observe similar behavior as double stiffeners. We can consider this at T section loaded in compression. And here we have a partially stiffened panel. We have this part is free and stiffened, and this part is stiffened. The observation showed that here with full length stiffener we have torsional buckling failure, and here we have a kind of flexural buckling. The partially stiffened panel on the central part and that with stiffeners on the tip ends of the panel show a flexural buckling on the free part. Free part is here. This one is double this free part here. The specimen with free parts at the end near the flange, this specimen, has a higher resistance than the other because its free part is smaller. This idea will be discussed at the end of the presentation in a parametric study, as the aspect needs to be discussed due to some experimental observation. As for the other specimens, the finite element model is close to that observed for tests, mainly for ultimate resistance represented here. The comparison of the all load displacement curves of the specimens from tests show the influence of the stiffeners on the curves and maximum load reached. The unstiffened panel, which is presented here, has the lowest resistance with the sharp decrease of load here after the maximum value. This characterizes the flexure instability with small plastic deformation. The fully stiffened panels, this one and this one, show the highest resistance with failure modes in torsional buckling. The partially stiffened panels show intermediate resistance. The resistance seems to be controlled by the free part of the panel, which is not stiffened, represented here with red circle. Here we can see an illustration of the flexural buckling in this part and torsional buckling of this panel, we can see that the finite element model represents well the failure mode. This is another illustration of the stiffened panel only on one side. We can observe torsional buckling here in the finite element model and the test. And here we have partial stiffened panel, and we can see that the finite element model represents well the flexural buckling observed on the reality. The two other configurations of partly stiffened panels on the two ends or on the center part showed also flexural buckling, and we can see that the finite element model represents well the behavior of the two specimens. On our first observation, the stiffeners welded to the flange saw the resistance lower than that welded only to the web. This one was lower to this one. But when we changed the configuration, the geometries, and we considered elements with higher slenderness, we changed the observation. That means the resistance of this specimen was higher to that of this one. A parametric study was performed to compare those two configurations. We changed here the slenderness of the element. The height of the stiffener is similar to that of the tested elements. And here we changed the length of the stiffeners. We can see that this configuration has higher resistance than this one in many cases. As conclusion, we can see that two test campaigns were performed to observe the behavior of web panels with and without different configuration of stiffeners. A finite element model was validated on the basis of those tests. Two failure modes were observed, flexure buckling and torsional buckling. The resistance of partial stiffeners depend on their dimension and position. This aspect needs to be more analyzed. All the results obtained in this study will be used to develop an analytical model to predict the strength of stiffened web panels, fully stiffened or partially stiffened. Thank you for your attention.